This video was made to explain the situation at Fukushima Daiichi nuclear power station as of September 2013. Fukushima Daiichi nuclear power station is located along the coastline of Fukushima Prefecture, facing the Pacific Ocean. 6 nuclear reactors stand at the site. Units 1 to 4 are on the south side, and Units 5 and 6 on the north. On March 11, 2011, when the Tohoku Pacific Ocean earthquake struck, Units 1 to 3 were operating, and Units 4 to 6 were undergoing periodic inspections. The intense shaking caused ceiling panels to dislodge and shelves to topple over. Circuit breakers in Units 1 to 4 switching station were damaged, and the power line tower of Units 5 and 6 fell over due to a collapse of the embankment. Consequently, the whole site lost its outside power source. A total of approximately 6,400 workers were working at the site. All were able to evacuate within the 40-minute time span between when the earthquake struck and the tsunami arrived, to the hill where the seismic isolated building was located, or into the main control room. It was 40 minutes after the earthquake that the enormous tsunami struck. The reactor and turbine buildings of Units 1 to 4 stand at a height of 10 meters above sea level. The tsunami reached the height of 15 meters, much higher than the assumed 6.1 meters. Water flooded into the buildings through the equipment hatch and the emergency diesel generator air supply louver. The power panels and the diesel generators installed on the first and basement floors were flooded, rendering them inoperable. The seawater pumps of Units 1 to 4, which were located 4 meters above sea level, were also damaged. Due to this damage, both the power supply and the seawater cooling function were lost. Units 5 and 6 reactor and turbine buildings are located at a height of 13 meters above sea level. They suffered less damage than Units 1 to 4. The emergency diesel generator B of Unit 6 was the only power supply in the power station which survived the tsunami. There was no direct damage to the building, as it was installed at a height of 13 meters above sea level. The generators transferred power not only to Unit 6 but also to Unit 5, which prevented the reactor cores in these units from being damaged. The cream-colored building with gray lines is the seismic isolated building. In July 2007, the Niigata-ken Chuetsu-oki earthquake struck Kashiwazaki-Kariya nuclear power station. This event introduced the idea of installing seismic isolated emergency centers at each power station site. Construction of Fukushima Daiichi nuclear power station center was completed in September 2010, half a year before the accident. The current number of workers at Fukushima Daiichi nuclear power station is approximately 3,000 per day. 200 TEPCO employees work inside the seismic isolated building. From this perspective, 35 meters above sea level, one has a bird's eye view of Units 1 to 4 reactor buildings. Various decommissioning work is in progress. The building covered with the white cover is the Unit 1 reactor building. As the upper part was damaged due to a hydrogen explosion, the whole building was completely covered to prevent dispersal of radioactive material. The cover was installed in October 2011. The building at the front of it, with pale blue and white patterns, is the Unit 2 reactor building. Unit 2 remains as it was before the accident, as it did not suffer a hydrogen explosion. Unit 3 is in front of Unit 2. The upper part of the Unit 3 reactor building was heavily damaged due to a hydrogen explosion. A gantry to support heavy machinery has been constructed at the site of the building to remove debris and prepare for fuel removal from the spent fuel pool. The work is being carried out remotely using cranes, as the radiation level at the top of the 5th floor of Unit 3 is too high for workers to stay for long periods. The building at the front is Unit 4. At the time of the earthquake, Unit 4 was under periodic inspection. The shroud of the reactor was being replaced, and all the fuel assemblies were stored in a spent fuel pool. In July 2012, 2 fuel assemblies were taken out for a soundness inspection and moved to the common pool. No major scratches or corrosion was found on the fuel assemblies or the fuel rods inside. A cover equipped with a crane to remove the fuel is currently being constructed at Unit 4 reactor building. The steel frame and the exterior walls and roof panels have already been completed. The ceiling crane and machinery to remove the fuel have been placed in this structure and are currently being assembled. Electricity line installation and operation checks are planned. Preparations are underway to start removing the fuel by November 2013. The spent fuel storage facilities at the site are spent fuel pool inside the reactor buildings, the common pool, dry cask storage building which existed from before the accident, and a temporary facility to store dry casks which was installed after the accident. The left of the 2 buildings is the common pool building, where the spent fuel from all the units is stored. The damaged equipment is being restored. The fuel currently stored in the common pool will be put into dry casks and moved to the temporary storage area. This area is a temporary facility to store dry casks. We are planning to start removing the fuel from the Unit 4 spent fuel pool from November 2013. The fuel is planned to be transferred to the common pool near Unit 4. The fuel will be removed to the common spent fuel pool near Unit 4, which is already at 90% of its capacity. This fuel in the common pool will then be moved to the dry casks and stored here. Under the mound is a temporary waste storage facility to store debris with relatively low-level surface radiation. The facility is covered with soil to lower the radiation levels at the site boundary. The debris gathered from the site and the upper part of the reactor buildings is sorted by surface radiation level and type of material and then stored at the site. The storage area is either covered by a building or by soil, depending on its radiation level. This is a circulation water cooling system, which was installed to recycle the water injected into the reactors to cool them down. After the accumulated water is collected from the basements of the buildings, radioactive materials and salt are removed through this system. This line was shortened from 4 kilometers to 3 kilometers in July 2013 by replacing the injection water tank from the buffer tank to the Unit 3 CST tank, which is located nearer to the reactor buildings. Reliability has been improved not only by the scale down of the line, but also by the increased capacity of the injection water tank and the seismic resistant improvements. The pipes laid outside the buildings are planned to be further shortened in the future. The steel cylindrical tank is the CST tank, which was installed before the accident. During normal operation before the accident, this tank was used to temporarily store water which was used inside that plant. We decided to use this tank as an injection water tank after it was confirmed to be intact. The water stored in the tank is injected into the reactors of Units 1 to 3 by the injection pumps installed inside each reactor building. This area is located at a height of 35 meters above sea level. These fire engine trucks are deployed ready for reactor water injection backup. We also conduct training to inject water into the reactors. This is a diagram of the water treatment facility. It was installed after the accident to decontaminate the water which continues to accumulate inside the reactor and turbine buildings. The main functions are cesium and salt removal. The system consists of the removal facilities, control rooms to operate these facilities, and tanks to store treated water. This is the process main building where the Areva decontamination facility is stored. The accumulated water transferred from the turbine building is stored in the process main building and the high-temperature incinerator building and processed through the treatment system, newly installed on the upper floors of the buildings. This is the incineration workshop building where the cesium absorption apparatus, Curion, is stored. The apparatus removes cesium by utilizing a special material called zeolite, which absorbs radioactive materials. This is the high-temperature incinerator building, where the second cesium absorption apparatus, SARI, is stored. The white tent-like building is the building for reverse osmosis membrane and the evaporative concentration facilities. These are facilities to desalinate the accumulated water after its radioactive materials have been removed. This building is the control room for the contaminated water treatment systems. The monitoring and operations are conducted all day and night, with 10 operators working in shifts on 24-hour schedules. The treated water is stored in tanks installed at the site. A total of approximately 340,000 tons of water is stored at the site. The capacity of the cylindrical tanks is approximately 1,000 tons. The long horizontal blue tanks have a capacity of approximately 100 tons. Dams are built around the tanks. Drainage paths are being made into closed conduits in case water from the tanks or the water lines should leak out. Currently, approximately 400 tons of water flows into the reactor and turbine buildings per day. The water which mixes with contaminated water inside these buildings is increasing and has become one of the most serious issues at the site. To prevent the amount of contaminated water from increasing, we are working on countermeasures, such as bypassing the power station by pumping up groundwater from upstream before it mixes with contaminated water, then discharging it into the ocean, and removing almost all the nuclides from the contaminated water through a system called the multi-nuclide removal facility. We are also progressively installing tanks at the site. This well is part of the groundwater bypass system. The system was installed to pump up groundwater from the mountainside before it becomes contaminated and discharge it into the ocean. One of the biggest issues at the site is that the amount of contaminated water is increasing at the site. The groundwater, which flows from the mountainside to the ocean through the site, flows into the reactor buildings. The groundwater bypass system helps to change the flow of the groundwater and reduce the amount flowing into the buildings. The groundwater pumped up by this system is stored in a tank and checked to confirm whether the radioactive material density is below the allowed target levels. So far, we have installed 12 wells to pump up the groundwater, a tank specifically to check the water quality, and dedicated pipes to transfer the water. Both the water in the well and in the temporary storage tank have been measured, and we have confirmed that the radioactive material density is sufficiently low. The multi-nuclide removal facility is installed inside this white tent-like building. This is the inside of the building. This facility reduces the radioactive material density of the already processed accumulated water to an even lower level. The existing water treatment system mainly removes cesium. However, this facility is able to remove up to 62 kinds of nuclides. The facility is currently undergoing hot testing using radioactive water. After its performance is confirmed, we will start full-scale operation. The total capacity of the tanks installed at the site is approximately 400,000 tons. We plan to increase the tank capacity to 800,000 tons by fiscal year 2016. In May 2013, high levels of tritium were detected from the groundwater in the coastal area at the east side of Units 1 to 4 turbine buildings. Monitoring of the surrounding groundwater and the seawater taken from the port was strengthened. As a result, we confirmed that groundwater taken from a certain part of the ground was contaminated. From investigations so far, we assume that the most probable cause is that part of the residual contaminated water, which leaked to the ocean through the trench in April 2011, has seeped under the trench and reached the surrounding soil. In addition, although there was no significant rise in the radioactive material density of the seawater inside the port, we found data showing that the groundwater flowing through the site is reaching to the sea. With regard to the impact of radioactive materials, we monitor radiation levels at various points and disclose the results of this monitoring operation. We believe that the impact on the surrounding waters is limited to the area within the port of the power plant, and that judging by the results of our monitoring 3 kilometers offshore, there has been no impact on the waters of the wider ocean. We are currently undertaking work to protect the ocean, such as removing contaminated water from the trenches, preparing to start the groundwater bypass system, and perform ground improvement of the contaminated area by injecting liquid glass, and a variety of other measures. Seawall construction work is also ongoing as a fundamental countermeasure. This is being built approximately 5 meters away from the Unit 1 to 4 intakes. Steel pipe sheet piles of over 1 meter in width are hammered into the seabed in a row in order to construct a barrier between the ocean and the groundwater. About 600 of these will be installed, extending to a total length of approximately 780 meters. Drainage facilities will also be installed to prevent the groundwater from flowing out from the wall to the ocean. The steel pipe sheet piles are due to be installed by March 2014. They will then be fixed with mortar and the drainage facilities will be installed. The seawall is due to be completed in September 2014. In addition to the seawall, a landside impermeable wall is planned to be constructed using frozen soil, and groundwater will be pumped up from the subdrain facilities as a fundamental measure. In August 2013, leakage was found at one of the tanks that stores concentrated water from which cesium has been removed. From the reduction in water level, we were able to confirm that approximately 300 tons has leaked out. A large amount is assumed to be seeping into the soil. We are currently investigating the cause. The water in the tank in question was immediately transferred to another tank. The contaminated soil is being collected, and patrols and monitoring have been strengthened.
福島第一原子力発電所長の小野でございます。まずはじめに福島原子力発電所の事故および汚染水の発電所港湾への流出やタンクからの汚染水の漏洩などによって今もなお発電所周辺の皆様をはじめ広く社会の皆様に大変なご迷惑ご心配とご苦労をおかけしておりますことを改めて心より深くお詫びを申し上げたいというふうに思います。本当に申し訳ございません。また事故発生以降政府関係諸機関メーカー等の皆様をはじめ国内外を問わず広く世界の皆様に多大なるご支援とご協力をいただき改めて心より深く感謝を申し上げたいというふうに思います。本当にありがとうございます。現在福島第一原子力発電所では徹底的な現場調査に基づく設備リスクの把握および運営管理上の問題点を洗い出し対策を検討して優先度を定め計画的に対策を講じてきているところでございます。一方で設備リスクが顕在化してしまった汚染水の流出などの問題につきましては緊急かつ最大の経営課題として重く受け止めており全社を挙げて解決に向けて取り組んでまいります。 現在避難されております住民の皆様の一刻も早いご帰還を実現し、地域及び広く社会の皆様の不安を解消するためにも、弊社は政府及び関係機関のご協力のもと、廃止措置に向けたさまざまな取り組みを進めております。今後も安全の確保が最優先との基本認識のもとで、廃止措置に向けた取り組みを着実に進めてまいる所存でございます。今後ともよろしくお願いいたします。